are in Statistical Rethinking, second edition. We're in the hard parts of chapter 11. We're on question 11H3 here. So, okay, so here's the question. There's two parts, but we'll read this first part here. So, the data contained in salamanders, the salamanders data set, are counts of salamanders from 47 different 49 square meter plots in Northern California. The SALAMAN column is the count in each plot, and the columns are percent cover and forest age. So it's percent of ground cover, I suspect, and how old the forest is. Well, in fact, it tells us what it is right here. So we are meant to model SALAMAN, again, which is the count of salamanders in each plot, as a Poisson variable. Okay. So there's two parts here, but we'll just look at them one at a time as we come to them, so we won't read them right now. But first, we have our data up here. So this is just the first 6 rows of it, but you see that we have different sites, which we won't use. But we have the number of salamanders in each plot at each site, percent ground cover, and forest age. Anyway, so it's going to come to pass that I don't know how either of these things is meant to affect anything. I have no intuition for any of this. So because of that, I'm going to standardize these variables here. Okay. Now, to be honest, I really don't know how many salamanders to expect in 49 square meters. So we could standardize this, but then we probably wouldn't be able to appropriately use a Poisson regression. So we're just going to leave that as is. And I am going to try to reason myself to a prior here. Okay. So I kind of detail how I'm thinking about how to set a prior for how many salamanders I expect to be in a plot, and then I'll try to back out priors for the other parameters. But roughly, I imagine that each little salamander needs some space. It's probably more than a square meter, but maybe not, I don't know. And maybe as much as 25 meters. I don't know that either, but these are just guesses. If I think about a salamander in the middle of a 25-meter radius, that seems like a lot of space for a little salamander, I guess. And then also the salamanders are going to be intermingling with one another. So that upper, 25-meter radius seems like maybe way too big. But so there's that. So if I think about a 49 square foot plot, that's about between 1 and 30 salamanders per plot. So the priors that I establish, I'm hoping will get me within that range. Okay. Again, I'm doing this on the basis of not having looked at the data, even though we've looked at the data here. Presumably, we've done this ahead of time. So, okay. Here's our first part of the question. So we're supposed to model the relationship between density, or count of the salamanders, and percent cover using a log link for a Poisson distribution, or for a Poisson regression, using weakly informative priors, and that's kind of what I was talking about up here. And so we'll use both quap and ulam and compare them against each other, and then we'll plot the predictions based on the model. Okay. So first we need to establish some priors here. Okay. And so what I've done here is just created a simulation that says, okay, well, here's my priors for my intercept. So, okay, my model is going to have an intercept and then a regression coefficient for percent cover. So I've created possible values of A for the intercept and for the coefficient for percent ground cover. Okay. Now, the way that I arrived at these was up here. Again, I assume that we need between 1 and 30 animals per plot, and so on the Poisson model, when we use a log link, here, I'm guessing that between maybe somewhere in the middle of 1 to 30 on the natural scale would be what I'm shooting for, but now this is going to be logged, or that number will be logged, and so it's going to be reduced. And so I tried a bunch of different values here and eventually arrived here as being reasonable. Okay, so that's kind of how I established the prior for A. And then for B, for the coefficient for percent cover, I assume that more ground cover is going to lead to more salamanders, I suppose, but I don't really know that, and so I'm centering a normal distribution around 0 here. Well, I've converted P into a standard variable, and so I don't really know where to put the variance, and so again I kind of arrived at this value iteratively. Okay, so I started at 1, went up and went down, and so on and so forth. Okay, so so let's just so this is the prior predictive distribution. Okay, and we can run this a few times and kind of get a sense for what the model expects to see. Okay, so we see values that when there's more and more ground cover that are up around 30. It has a weird consequence of having less really low ground cover as also having an increase, which seems weird, but hopefully that gets sorted out with the model running. But let's just see what happens when we try some different values here, right? So if I change the variance here, for instance, now we get some really kind of probably outlandish values, I'm guessing. And so so we set that there. We can maybe increase this. And you see, these values don't at all seem correct to me. They seem too chaotic and extreme. And so it was just a process of that before I, eventually arrived at these as the priors. Okay. So, so those priors are reflected here in the model. And again, we're supposed to run both quap and ulam. So I'm just defining one model, and then I'll pass it to the two functions here. So we have SALAMAN, and it is a regression as a Poisson variable. So it's distributed as a Poisson with parameter lambda. Okay, and then the log of lambda, which is the expected value of a Poisson distribution, has this linear model here. Okay, and then that linear model has the priors that we already discussed. Okay, so I've already ran this for both models. Okay, and so here's the Preci output. And if we look at the two models, the quap function is doing pretty well comparing to the ulam model. And that's really a function of the time we took to establish good priors here. Okay, so if we had more lenient priors, we should expect the comparison to get worse and worse and worse. Okay, now we are supposed to kind of plot the predictions of our model, and I'm just going to use the ulam model, but we're supposed to plot those predictions against the actual data. Okay, and so here's the code to do it. So I'm defining a range of values for percent cover in standard deviations from -3 to 3, which should cover 99% of that interval. Okay, and then I'm calculating the expected value at each value of p. Okay, with the link function, and then also the percent, the credibility intervals, the symmetric HD, or the symmetric intervals. Okay, and so now I will plot the actual data against, well, the actual count against the actual percent, or the actual variable p, or percent cover, standardized percent cover, and then I will add a line that is representing this function up here. Okay, that's representing the mean of our model prediction, and then I will also put the error, the credibility interval around that prediction. Okay, and so oh, that's weird. I've broken something. Hold on. Okay, now we're back. I had ran some code later that I must have duplicated some of the names, and it messed this part up. So anyway, but this is the actual data in little dots here, and then the fit of the model. Okay, and so the fit of the model, it seems to be doing okay capturing the mean, value, but this is also meant to capture all the data, and you can see how overly variable and dispersed the data is, especially as we come further and further out in percent cover here. I also don't know that it's doing a great job of capturing these values here. It seems to want to predict higher values than what is actually there. It has trouble saying that there's no animals there, I think. So, okay, so that's interesting or whatever. We will learn a different way of representing this data, of modeling this data later that captures more of this variability. It's called a negative binomial model, or I think maybe it even goes by, I can't remember the other name, but we'll learn how to deal with this later. But for now, we are meant to try to improve this model by adding forest age as a predictor. Okay, so that's what we'll do. But the first thing we're going to do is try to modify the priors. Why? Okay, the reason we need to modify the priors here is, let me go back up here. Okay, so we're going to have another term now, and it's going to be for forest age. Now, so Poisson models typically use this log link function, which means that to get back to the kind of natural scale, we will exponentiate everything, which means that this term on the natural scale is A times BP times P times da 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 da. So in other words, another term is not going to have an additive effect on the natural scale. It's going to have a multiplicative effect. Okay, and that could, well, because of that multiplicative effect, adding another term in here, if we were just to use the same priors, right? Now we have BF in here, and let's say that we use the same prior, it will probably be more permissive of extreme values, and so we may not want that. Okay, so well, let's just put them all at the. Okay, so let's have everything kind of at the initial values. Okay, and now notice how more extreme values are permitted everywhere. Okay, so instead, what I used was 0.3, and went with it. And this seems to kind of constrain things again. You can play with this and whatever, but that's how I arrived at modifying the priors. Okay. Okay, so now we'll just continue with ulam. So I have the model here, and I've already ran it, so we don't have to sit here and watch that. Okay, so does this make much of a difference at all? Well, not really. So if you go back up and you compare the Preci outputs to the first model we ran, the coefficients for A and BP are pretty similar. BF differs, or BF was not included in the first one, and now we do have it in here. And notice that it very much straddles 0. It's around 0, it straddles 0. And this probably makes sense because I suspect that the percent ground cover and the age of the forest are probably pretty highly correlated with one another, right? But anyway, I also want to plot the predictions again and see if this is, if these small differences that are, found in the model have any consequence in the predictions of the model. So we have everything identical again. So we're going to predict across all values of P as well as F. So we'll just make another plot for F. But I am going to lay these predictions on top of the previous predictions. So I'm going to plot the raw data, and then I will have two sets of lines, one for the original model and one for the new model. So we run that, and so this is what we get. So let's just focus on the top one here. So again, this is predictions across values of P, percent cover, and the two models are basically right on top of each other. So adding this additional variable did not do much, as we might have expected. Now, if we look at the predictions based on different values of F, this model seems to be doing just a horrible job. But it kind of makes sense that it's doing a horrible job because it does not seem that F is really all that important in our model in the first place. So, okay, we will call that good.